Today we are very happy to have Stanford, who will tell us about chaos and black holes.
Okay, thank you for the invitation to this very nice workshop. So I want to start by writing a couple of very basic formulas so that we can agree on some notation. So this has nothing to do with black holes, just formulas for quantum mechanics. So we'll call z of beta the thermal partition function, trace e to the minus beta h. Beta is the inverse temperature. And to compute this thing, we'll think about putting our quantum mechanical system or quantum field theory on a manifold where the time direction is a circle of circumference beta. So the thermal partition function is associated to this circle of circumference beta. And if we were to compute this in a higher dimensional theory, let's say we have a quantum field theory on a spatial sphere, a d-1 sphere, then we would choose a manifold which has this circle here, this beta circle, and also has this sphere. This would be an S d-1. And we could replace that sphere by whatever geometry. Let's see, what else? So if we compute a two-point function, so trace e to the minus beta 1h times some operator, e to the minus beta 2h times some operator, that would be associated to changing this circle so that we have 2 points on the circle where these W operators are inserted, and we have time beta 1 here and time beta 2 there. Okay, and another thing that will be useful is if we start with this thermal partition function and we cut it here. So we take the path integral on this manifold and we cut it here. Then we get a Hilbert space that consists of two copies of our quantum mechanical system in an entangled state. That is the thermal field double state, which is the sum over all the energies e to the minus beta over 2 times En times n. So the thermal field double state is what you get by cutting this partition function. Okay, I think that's it for this. Hopefully these notations are clear. Okay, so this talk is about black holes and quantum chaos, and I want to start by explaining some symptoms of many-body quantum chaotic systems. So here are four properties. So I'll just go through them briefly, and then we'll eventually move on to black holes. So one symptom of quantum chaotic systems, in particular many-body quantum chaotic systems, is that two-point functions decay with time. So if we compute a thermal two-point function of an operator at time 0 and operator at time t, then we get some time dependence that looks roughly like this. It could oscillate, but it will decay with time. And this is a probe of a type of thermalization. The two-point function decays. You can think about this two-point function as like the amplitude that if we create this disturbance at time 0, it will still be there at a later time t. And in a quantum chaotic system, if you create a little disturbance somewhere, it's just going to thermalize and disappear. And that's why this two-point function decays. Okay. In some sense, this is the most basic diagnostic. Something a little bit more complicated, but also interesting, is that these out-of-time order correlators also decay. So an out-of-time order correlator, that's the thermal expectation value of a product of some operator v at time 0 and some other operator, or it could be the same operator at time t. V of 0, W of t, V of 0, W of t. And the behavior of this thing as a function of time looks something like this plot in a many-body quantum chaotic system. It's approximately constant for a while, And the approximate constant answer is just the product of two-point functions. Like, forget about the ordering of these things and just take the product of a VV two-point function, a WW two-point function. That's this approximately constant value. But then after some time, it starts to decrease and goes to 0 at late times. Or it becomes small in any case at late times. And as we'll explain a little bit more later, this is a symptom of the butterfly effect. Or this is like a definition of the butterfly effect in quantum mechanics. Okay. A third aspect, the third symptom of quantum chaotic systems is that the energy eigenvalues satisfy random matrix statistics. This is the Bohigas-Giannoni-Schmidt conjecture. And the idea is that if you look at the actual numerical energy eigenvalues of a quantum chaotic Hamiltonian, then after accounting for whatever symmetries you might have, those numbers have statistics that resembles that of the eigenvalues of a random matrix. This is sometimes also known as random matrix universality. So this is sometimes called random matrix universality. And the final one that we'll discuss a little bit is that, so this is about the eigenvalues of the Hamiltonian. There's another statement about the eigenvectors of the Hamiltonian, which is that they look, in some sense, we'll describe a little bit more like random vectors. And this is part of what's called the eigenstate thermalization hypothesis, or ETH. Yeah. It depends. It depends on the symmetries that the Hamiltonian has. So you can have different random matrix ensembles for different classes of symmetries. Yeah, that has a, well, maybe ask me about that more when we get to the gravity discussion if you want to hear about how that works in the gravity. I was not planning on discussing that. Okay. All right, so these are four symptoms of quantum chaotic systems. And there are many questions. For example, what are the timescales associated to these things? Are there, how small of a region do you have to look at so that the random matrix statistics are good? Like, how random are these eigenvectors? Some other questions are like, are there relations between these? For example, can you have some system that has some of these properties but not other properties, and which ones? Are there implications between them? And a lot of these things are not known. It's in some sense a sort of phenomenological theory. The reason that some of these things are not known is that it's hard to study many-body quantum chaotic systems. And here are some methods that people use to analyze them. So one method you can use for not that many of many-body quantum chaotic systems is you can do numerics, either exact diagonalization numerics or some kind of tensor network or matrix product state, matrix product operator numerics. Another thing that you can try to do is prove general bounds. So this could be, for example, exact diagonalization, matrix product states. For bounds, there are bounds like the Lieb-Robinson bound. There's this chaos bound. And you can hope to prove general bounds about these properties. You can study solvable models, or sort of solvable in some approximation. An example of this is the SYK/Slavchev-Kataev model. Another example is you can kind of push the chaotic system almost out of the regime of chaos into weak coupling, where it's only very weakly chaotic. That's not really the problem you want to study, but it's something where at least you have a handle on it using perturbative quantum field theory, quantum mechanics. And the last method is to use holography. And that's what we're going to discuss today. So the idea with holography is that it's that certain black holes represent certain many-body quantum chaotic systems deep in the strongly chaotic regime. So in some sense, it's a little bit like the SYK case, if you're familiar with that, but not with holography, maybe. So in the SYK case, you have some interacting fermion system that after ensemble average is described by a collective field theory of some bosonic fields. So there's some collective description. And that collective description is useful, particularly in the limit of many, many fermions, the large N limit. The black hole in holography is a type of very interesting, very beautiful collective field description of certain strongly interacting quantum many-body systems. Okay, so so it's both a many-body system and it's strongly interacting. So there's two separate properties there. And so to explain these parameters, in the most sort of famous example of holography, we relate those parameters of the boundary theory to properties of the bulk theory as follows. So the number of degrees of freedom in the boundary theory, so that's supposed to be large to have a many-body quantum system, that is proportional to 1 over the gravitational coupling in the black hole theory, in the bulk theory. So if the gravitational theory is weakly interacting, G Newton is small, that's where we can do calculations, then we have a very large number of degrees of freedom in the boundary theory. So that is sort of, that is a common feature of these collective field descriptions. That's also true in the SYK model. Okay, and the other parameter is that there's a interaction strength in the boundary theory. And it is proportional to 1 over a power of the string length in the bulk theory. So if strings are small, which means basically we can use point particle theory, quantum field theory coupled to gravity. If strings are small, then that's the easy case to analyze in the bulk. That means that the boundary theory is strongly interacting. So the easy to describe black hole is the case where G Newton is small, and that means the number of degrees of freedom is large, and L string is small. That means the coupling is large. So it's precisely pointing us towards this many-body, strongly interacting regime. Okay. So what do we gain by studying quantum chaos through using this tool? So the thing that I kind of like about this subject is that there's two different interesting things that are happening. So one thing that is happening is that black holes are teaching us something about quantum chaos, and a little bit the other way also. And I would say that is basically how these two examples work. So we're exploiting this holographic duality to learn something about quantum chaos by doing black hole calculations. And the other examples, I think it's fair to say, basically work this way. So we use some facts about quantum chaos or some conjectures about quantum chaos and learn something about black holes. And there's a little bit going the other direction as well. But the primary flow of insight is this way for these two examples, A and B, and that way for the other two examples. And that's great. We get to learn something in both directions. Okay. Questions about this setup? I hope people will interrupt, because if you do not interrupt or ask questions, we will end, well, maybe it's fine, we will end early. So don't worry that we will delay too much if you ask questions. Okay. Okay, so here's the plan. I'm going to explain the black hole geometry. Then we're going to use it to go through these 4 examples. So let's discuss the black hole geometry. We're going to start with what's called the Euclidean black hole, or imaginary time black hole. So this is a black hole whose purpose in life is to help us to compute the thermal partition function of its dual quantum mechanical system. So remember, underlying all these examples is there's some kind of quantum mechanical system that is secretly described by a black hole. So the purpose of this Euclidean imaginary time black hole, which I'll explain in a second, is to help us compute the thermal partition function. of the quantum mechanical system, z of beta. So that's that thing up there. And we're going to use this notation grav for like gravity computation of, which means you use the black hole to compute this thing. So some slightly awkward notation, but hopefully it's clear. And so to compute the thermal partition function, z of beta, we want to apply this gravity computation to this type of boundary computation. So the red circle represents the periodic imaginary time in the boundary theory that computes the thermal partition function. We're trying to compute this thing using some gravity rules, which we'll just discuss. I'm first going to draw pictures for you for the case where the bulk theory has 2 space-time dimensions. And the boundary theory, so the black hole is like a 2 space-time dimensional black hole. The boundary theory has 1 dimension. So space-time dimension, 1 space-time dimension means it's just time. So it's quantum mechanics. Okay, so what does the geometry look like? So we take this red circle and we make it super big. This is the rule for how you compute it using a black hole. You take the red circle that corresponds to the imaginary time of the boundary theory, you make it super, super big, and then you fill it in with a solution to Einstein's equations. So the solution to Einstein's equations for the type of black holes that we're interested in, Einstein's equations with a negative cosmological constant, so r mu nu should be minus some multiple of the metric. This is a Ricci curvature tensor, should be minus the metric tensor. And you solve those equations subject to the condition that way, way out far away, it becomes a really huge circle. Okay, so the topology of the 2-dimensional thing we're computing, that we're finding, it's a disk. It's the topology of a disk. And it's supposed to have negative curvature. And a disk-shaped thing with negative curvature in 2 dimensions, that has to be this Poincare disk, hyperbolic space. So I'm sure you've seen these pictures of the angels and demons or whatever, the Escher picture of the hyperbolic plane. The idea is that all of these circles should have the same size. So there's some big infinite number of circles that go out to the boundary, and the metric is such that they all have the same size. That's hyperbolic space. And here's the metric. So rho is a coordinate that starts at 0 in the middle of the disk, and it goes to infinity at the boundary of the disk. And okay, so this is moving in the rho direction, and each circle you cross, you like tick off 1 unit of distance. So there's an infinite number of circles you cross, there's infinite amount of distance between rho equals 0, rho equals infinity. And this metric is such that if you look at the circles, let me draw one at constant rho, these things, then the circumference of those things grows super fast with rho. It's like sinh of rho, 2 pi times sinh of rho. So that's the geometry of the hyperbolic plane, hyperbolic disk. And this is a Euclidean black hole. So remember that we identified the boundary of this thing with a inflated version of the boundary manifold, this Euclidean time manifold where we compute the thermal partition function. So we can identify the angular coordinate here with 2 pi over beta times the Euclidean time of the quantum mechanics theory. So that's the Euclidean time that goes around that circle up there, that goes from 0 up to beta. And if tau goes between 0 and beta, then theta will go between 0 and 2 pi. So that's the identification between the boundary time coordinate and the angle in this Euclidean black hole. So in particular, the rotation symmetry of this solution, which is a translation in theta symmetry, is related to a time translation symmetry. And this fact and a cousin of it is going to be important later. Okay. All right, so let's now discuss what happens if we do this in higher dimensions. So if we do it in higher dimensions, then we're supposed to start with, instead of just this circle, we should start with, let's say, this thing. And the way the gravitational problem works is you take a copy of this, you make it super, super big, and then you fill it in with a solution to Einstein's equations. So the topology of the way of filling it in that corresponds to the black hole is this one here, where you fill in the circle that corresponds to the imaginary time. So that's the defining property of a Euclidean black hole. It is a solution to Einstein's equations that fills in the time circle in a way that it's contractible. So this red circle here that corresponds to the imaginary time, it is contractible here. And the topology is this, but the geometry is not a product. The actual geometry will be something of this form, where we have d rho squared plus some, the size of these theta circles varies in some way with rho, and in particular gets very, very big as rho goes to infinity. So some function that generalizes our sinh squared. And then some other function which determines the size of this sphere as we move in rho. And that also goes to infinity as rho goes to infinity. So the actual Euclidean black hole is a solution to Einstein's equation, so it's some differential equation you have to solve to pin down this f of rho and g of rho. Okay. Now, what is the point of this? Let's see. Now I'm getting in trouble because I do not remember what I've written and what I have not written. I probably have not written this part. To sort of finish the computation, the way that you do it is you evaluate the gravity path integral on this black hole manifold. So in a leading approximation, that would just be e to the minus the action, classical action of this solution. And this computation here is where you learn about the thermodynamics of the black hole or the quantum system that the black hole is describing. And this is, for example, where the formula comes from that the entropy of the black hole is proportional to the area. It comes from applying this, this logic here, computing the action of this solution. Okay, that's it for imaginary time, this Euclidean black holes. Any questions about this? Okay. So let's move on to real-time black holes. So Lorentzian black holes. To do this, we start with our Euclidean solution. I'm going to stop drawing the circles. Just this is the hyperbolic disk. We start with this thing, and we pick a time reflection symmetric slice. So this, or a reflection symmetric slice. So this slice here, for example. And then we start from this blue slice, and then we analytically continue in the angle. So we take theta to I times t. We start from this geometry, and we move in theta in an imaginary direction. So there's kind of two components of this slice here. There's one where theta is equal to 0 plus it. That's this part between the origin and the right boundary. And then there's another component where theta is equal to pi plus I times t. And that's this component here between the origin and the left boundary. Okay, so you take that geometry and analytically continue it in theta according to this rule. And this is the geometry that you get. This is the geometry that you get. This is the Lorentzian signature, Minkowski signature black hole. So this is a space-time diagram where time goes up and space goes sideways, and it's what's called a Penrose diagram. So it's been rescaled so that light rays move at 45 degrees. And let's try to understand what's going on with this geometry. So first of all, this slice here that goes straight across. This is the same geometry, exactly the same geometry as this blue slice. And starting from that blue slice over here and moving in theta, the theta equals 0 plus I times t is this region here, and the theta equals pi plus I times t is this region here. So if we make a time translation to this slice, then we end up with a slice that looks like this. And a further time translation, we'll get a slice that looks like this, and so on. Because of the way the diagram has been rescaled, you can fit an infinite number of these time-translated slices, and they kind of accumulate. They accumulate here. Okay. So time translations of the Euclidean black hole, they corresponded to rotations, like rotations of this disk. And time translations in Lorentzian signature correspond to like the analytic continuation of a rotation, which is a boost. It's a Lorentz boost. So the time translations that are mapping these surfaces into each other are Lorentz boosts. And the rapidity of the boost is it's basically t. So now we should be a little bit more careful. It's 2 pi over beta times t. Because when I wrote this theta, I should have written I times 2 pi over beta times t. And that's the same factor of 2 pi over beta that we had on a previous board. Okay, maybe I should move that one up so you can see. It's the same as this one. Okay. So let's explain a couple of properties of this geometry. One property is that if you look at this blue slice here, or any of the white slices you get by acting with a time translation, that thing has two boundaries. In other words, it intersects the red locus, which is identified with the space of the dual quantum system, in two places, once on the left and once on the right. And those two boundaries correspond to two copies of the quantum system. So really what this geometry is describing is some state of two copies of our quantum system. It's an entangled state. It's the thermal field double state. It's that state up there. So this is the statement that this geometry really describes the thermal field double of two copies of the black hole, of the quantum system dual to the black hole. And those two copies, their respective time evolution corresponds to this red manifold on the left side and the other one on the right-hand side. There's a beautiful connection between this space-time geometry and quantum mechanics. Like, we'll discuss some of those in the context of chaos. But there's another one that doesn't really have to do with chaos, but it's so beautiful, I have to explain it. You've probably heard it before, but if not, I should explain it, which is that this geometry encodes the fact that entanglement does not allow signaling. These two systems on the left and right are in this entangled state, thermal field double state. So they're entangled, but they're not interacting with each other. And so that means that if we start with some perturbation, if we create some signal on the left system, it should not be able to affect, on the right system, it should not be able to affect the left system. And the reason that is true is because light rays move at 45 degrees, nothing can move faster than light. So the most our perturbation can do, the best it can try to do to get to the left side is follow this trajectory. And it does not make it to the left side. So the fact that it does not make it to the left side because no point on the right boundary can make it to the left side, because the left and right side are protected or isolated by a horizon. So these lines I'll draw in solid green. These are the two horizons. So the left system is behind the horizon from the perspective of the right side, and the right side is behind this horizon from the perspective of the left side. So that is this point, which was made in this ER equals EPR paper by Maldassine and Susskind. Okay. So we're going to be interested in computing correlation functions using this black hole geometry. And the rule for computing correlation functions is the following. So remember what it looks like if we try to compute a correlation function here. We take our manifold of imaginary time and we insert a couple of operators. So if we apply this, I'm not sure, sorry, I'm not sure if you can read this over here. What I wrote was grav, like gravitational computation of, and then this, I basically drew a copy of that thing. And the computation of that is, in black hole language, you take this manifold, blow it up, use it as a boundary condition, fill it in, and so we get the black hole geometry, which is this thing. And then we have two insertions at the boundary, and they have to be somehow correlated with each other. So we compute a correlation function between these two field operators very close to the boundaries in the black hole. And we can think about this exact same quantity either as this Euclidean path integral or as an expectation value of W, an operator on the left system and an operator on the right system in the thermofield double state. This, I'm sure, is a useful kind of identity in all of our respective fields. And in the black hole picture, what it means is you can either compute this correlation function like this, or you can compute it like this. So you can think about it here as a correlation function of some operators on the two different Lorentz signature boundaries, or you can think about it here as a correlation function in this Euclidean geometry. Okay. Okay, so we're done with the explanation of the Lorentzian black hole, and now we're going to move on to studying these properties. We'll start with this two-point function. Any questions about what we discussed so far? My goal is to make the actual geometry, you follow the actual geometry. So I constrained myself in selection of these topics by not introducing like a new geometry for every topic. So we're only basically going to use this geometry. And we'll use this geometry for each of these. I'm lying slightly about part D, but basically use this geometry for each of these parts. So I want you to be comfortable with this geometry. And if you, I can try to answer a question now. Maybe everybody was already comfortable with this geometry. I don't really know the composition of the audience very well. Okay, so we're going to start now to compute this, the two-point functions. So to compute the two-point function in real time, here's what we do. We start with our Lorentzian black hole with our two boundaries. And we insert an operator W at time 0 on one boundary. And we insert another operator, could be on different boundaries, but for simplicity, let's just put them on the same boundary. We'll put another operator W of t at some time t later. And what we were trying to compute this two-point function, we want to compute this correlation function in the bulk theory. Now, I remind you that in the regime of interest, where the boundary theory has many degrees of freedom, the bulk coupling is small. So that means that the perturbations that the W operators create on the black hole, they basically are free fields. They do not interact with other stuff. So they're moving on this curved black hole background, but they're not interacting with anything. They feel the curved space-time geometry, but they don't interact. And if the coupling is large, then we don't have to think of them as strings. We can think of them as point particles. We use quantum field theory. The computation that you need to do in this large many-body, strongly coupled limit is a free field computation on the black hole geometry. And basically what happens in the free field computation is you act with a field operator here, creates a particle. The particle pretty much falls into the black hole. And so it's not there later. So it has, a little bit more precisely, has basically a constant probability per unit time of falling into the black hole. And that means that the two-point function, the amplitude that it remains outside, decays exponentially. So that's how we get the decay of the 2-point function and the thermalization. It's just because the particle falls in. So and it can fall in with a constant rate per unit time. This implies exponential decay of the 2-point function. Okay, so an example of a formula, just so you have a formula in mind, is for this case of a 2-dimensional black hole, the hyperbolic plane, then the 2-point function w of t, w of 0, it's like 1 divided by I times sinh of pi t over beta to the 2 delta, where delta depends on the operator w that we choose. Depends on what kind of free field is associated, what mass of free field is associated to this particle, to this operator w. So it decays exponentially. This is an easy computation to do, but I will not do it unless somebody wants to see it. We can expand this expression at large time, and we find that it is exponentially decaying with some, yeah, so what do? We expand it like e to the minus I omega t and see what spectrum of omegas appear in this function. And the omegas that appear are 2 pi over beta times delta plus n times minus I. So these are the spectrum of different decays that are encoded by this function. And the leading behavior at large time is just the n equals 0 mode, which decays like e to the minus 2 pi t over beta times delta. Okay, so this example is very easy for this hyperbolic space because you can actually write down the function. For the more interesting black holes, higher dimensional black holes, like okay, like the one with the f and g functions. Typically, you cannot compute the function exactly, but you can numerically compute these numbers here, which are called quasinormal modes. So higher d, you cannot compute this thing exactly, but you can compute the quasinormal modes. And that's a typical kind of quantum field theory in curved space-time problem, where you study the effective potential that this particle fields due to the curvature of the space-time and the angular momentum that it might carry. And you solve the wave equation numerically and find the spectrum of numbers that describe the decay of the 2-point function. There's a kind of interesting alternate perspective on these quasi-normal modes, these numbers that describe the decay of the 2-point function, which is that they can be thought of as eigenvalues, as a type of eigenvalue problem. So let's draw again our Lorentzian black hole. And we'll define the operator k to be the time translation operator that goes up this way and down that way. So the boost generator. And if you look at the spectrum of k in the acting on the Hilbert space of a free field in the bulk, then it's like the spectrum of a Lorentz boost. And this is a Hermitian operator, but it has a continuous spectrum. The spectrum of this k is a continuous spectrum of real numbers. But if you take k and adds a little bit of some other term, I will not describe this in too much detail. This is from a paper by Chen, Ivo, and Maldacena. Then this thing, the eigenvalues of this thing, are the quasi-normal modes. So there's an interesting parallel between this and classical physics. So in classical physics, if you think about the distribution on phase space, then if you do time evolution to that thing, you get some other distribution on phase space. I think the operator that takes one distribution and maps it to the other one, I think this is called Frobenius-Perron operator, something like that. It's a linear operator, and in principle, it is unitary. And so its eigenvalues are phases. So that's like e to the I k. Its eigenvalues are phases. That's like saying that k had real eigenvalues. But if you take that Perron Frobenius, or whatever it is called, if I forgot the wrong name, if you take that linear operator and you coarse grain it a little bit, then, and it doesn't matter too much exactly how you coarse grain it, but if you coarse grain it a little bit, then you get a non-unitary operator. And its eigenvalues are what are called these Ruel resonances. They describe the decay of two-point functions in this classical system. So what's happening here is a little bit similar. So you have some operator that formally is Hermitian or unitary in the two cases, depending on whether we take the log, and you coarse grain it a little bit, or you add a little perturbation, makes it non-unitary or slightly non-Hermitian, and then its eigenvalues become these quasi-normal modes or Ruel resonances. So that's the kind of connection between this idea and some older ideas in quantum chaos, classical chaos. Okay. Right. Okay. Sorry. Two other things that I should say about this two-point function, which is that if you study the two-point function of an operator that corresponds to a conserved quantity, or an operator that overlaps with a conserved quantity, then you find that the decay is slower, and depends on whether you're in compact volume or infinite volume, whether it becomes a power law or becomes exponential decay with a small decay rate. But basically what happens is that associated to conserved quantities, there's a special set of quasi-normal modes such that the imaginary part of these quasi-normal modes is like minus some number divided by the size of the system squared times something. And these coefficients are related to transport. So you can understand properties of transport in the dual many-body quantum system by studying the spectrum of these quasi-normal modes. And that's been a very interesting research avenue in holography. Finally, my favorite thing about the two-point function is this. So let's go back to this picture, the original picture. So the two-point function decays because the particle falls into the black hole. And that is sort of just like obvious from the description of this as a black hole. But there's something else which is more subtle and I think more more interesting, which is that the particle is still there. So from the many-body quantum chaos perspective, you make a perturbation, you wait a while, and like what? The perturbation is no longer there, it's thermalized. But in the gravity picture, it's somewhere. It's not like the particle has, something too crazy has happened to the particle. It is somewhere, it's just close to the horizon, or depending on your time slice, behind the horizon. And I would love to understand what that means in just quantum information language, just purely from the boundaries. What is this sort of sharply defined thing? The particle still existing later, just inside the black hole. What does that mean in the boundary perspective? So I think we have not understood that. Okay. Okay, we're done with the two-point function. We're going to move on now to the out-of-time order correlated. Yeah.
You have this gap delta, different quantity, different. That's the decay of the two-point function, and the leading decay of the two-point function at long times. And different quantum mechanical systems will have different deltas.
Yes.
And you told us a little bit about what goes into that, but is there more to say about that?
Well,
thinking about the quantum mechanical system.
Right, so there's more to say about that for the fields that correspond to conserved quantities, like components of the metric or a gauge field. Okay, like you have in mind like some kind of bound. You would like some bound or?
Well, or what are the ingredients that go into setting it?
Oh, for a scalar field, yeah.
More understanding of the ingredient. You've told us a little bit about what goes into setting it, but is there more understanding of it from this point of view?
From the graphic point of view, what goes into setting it is like the type of field, so like its Lorentz representation or spin, and its mass. Those are the most important things that go into setting it. It tells you what kind of free field it is and what wave equation you're solving. And then you just solve that wave equation. So the mass is a parameter in the wave equation, and you put that in, and you solve to find these quasinormal modes. You can solve for them analytically if the
Equations could have bound states, or you can have interesting structure in there.
I mean, the quasi-normal mode is kind of like a bound state. It's so the type of potential that you're solving, that you're studying, is a potential like this. So you can transform the wave equation into an equation like dx squared psi plus v psi equals 0. This type of equation for a potential that looks like this. So this is the boundary, and this is the horizon. And the height of this thing depends on the angular momentum of the mode of the field you're studying. And basically, the quasi-normal modes describe something that is sitting kind of over here, and it is slowly leaking out that way. And that's a slightly more detailed picture of what they are. So to actually compute the numbers, what you do is you put boundary conditions for this wave equation where the function should be, let's say, 0 at the boundary, and it should be purely ingoing over here. And you try to solve this problem to find eigenvalues of that with those boundary conditions. Maybe something else I should say, which is, I think, sort of a mystery from the perspective, as far as I know, sort of a mystery from the perspective of many-body quantum chaos, is that if you consider these operators on the boundary that have high angular momentum, then they decay very, very slowly. So in particular, if we take the space to be a sphere, so take the space to be a sphere, and we consider an operator that is smeared against some very high angular momentum spherical harmonic on the sphere, then it decays very slowly. And the reason is that it's like creates a particle in the bulk that's orbiting around the black hole. So it's in some perfectly happy orbit far from the black hole, and it doesn't really want to fall in. And it only falls in because of some kind of tunneling process or gravitational radiation. So the decay becomes very slow. I don't know if that sounds like a qualitative phenomenon. I don't know if that has a understanding from many body side. Sorry?
It was suggested that quantum scars.
Yeah.
High angular momentum.
Yeah, there's a paper by Dodelson and Zhibryedov, I guess. Is this the paper, the right reference, or?
It's another one. I'll tell you.
Okay, sorry for not remembering the correct reference, but yeah. In case you didn't hear, so Igor was saying that there's a suggestion that these sort of long-lived, rapidly rotating things are related to many-body quantum scars. Okay. Other questions? Yeah.
When you write down this two-point function, I would think it's completely fixed by, if we consider thermal conformal two-point function, it's the same expression.
Yeah.
But in that case, we can just think of it as a due to a thermal pure ADS, not a black hole. So how that coincides with...
No. So one is okay. No, the pure ADS contribution to this one is not is not exponentially decaying. Yeah. Okay. Okay, so let's discuss the 4-point function.
Explanation of why the 2-point function decays like not very sharp, but in the picture of the geometry, the particle falling into the black hole. It seems that it's a more sharp picture, but the 2-point function not very sharp drop.
Oh, yeah.
Yes. It's because the particle is described by a quantum wave function. So the picture I drew is sharp. It's like here's a particle, it falls in, and then it's not there. So the 2-point function should like very rapidly go to 0. But this particle is described by a quantum wave function on the geometry. And the quantum wave function is sort of spread out. And it is sort of, it's leaking into the black hole. But that leaking process takes time. So there's some amplitude that it remains outside. So it's like the particle sitting in that potential, this potential sitting here. And the wave function is leaking this way, but not, yeah. Okay. Okay, so the 4-point function we're going to consider is this out-of-time order correlator. V of 0, W of t, V of 0, W of t, thermal expectation value. And this thing we can think of as the inner product. Let's say V and W are Hermitian. Inner product of two vectors, V of 0, W of t, acting on the thermal field double, and W of t, V of 0, acting on the thermal field double. So it's the inner product of these two vectors. And if W and V commute with each other, then the inner product will be, let's say 1. Let's say, suppose we've normalized it so that it will be 1 if they commute with each other. But if the time becomes large and the butterfly effect happens, then any perturbation will fail to commute with any other perturbation by a large amount. And that means that these states will be quite different from each other. And so the inner product should go to 0. So that is why the OTOC is a measure of the butterfly effect. OK, so to calculate it in the black hole, what we need to do is think about these two states, and then see how to compute their inner product. So yeah, this is where it's maybe a bit of a disadvantage to be giving a Blackboard talk. I'm going to do an animation. OK, so this is the black hole geometry, each of these things. I can draw the horizons. I can make this look a little nicer, like the singularity. But I won't keep doing that. This is the Lorentzian black hole geometry. And so we start with the thermal field double state. We're trying to construct these two states. So let's pick this one. Let's try to construct this state. So we start with a thermal field double. Let's act with an operator at time 0. So let's say that time 0 is here, and time t is up here. So let's try to understand what this state looks like. OK, so to do that, we should act with an operator at v of 0, and it creates a particle. Again, it's a particle with a wave function. But the center of the wave function moves in like this, falls into the black hole. So that's what that state looks like. Now we want to create W of t, V of 0, thermal field double. So we should act with this, on this state with an operator at time t. And it's convenient to do that to look at the geometry at this time here. So draw a slice through there. Because then the V particle is way inside. We don't need to worry about it. And to act with the W perturbation, we just add something over here. So that means that it looks like we have the V particle over here. And now we're going to add another particle over here, which is the W particle. So that is what this state looks like. And from the perspective of scattering theory, this looks like an out state. It's where we've described the state in a simple way in terms of particles kind of in the future. So this is what I'll call out. OK. Now, sorry? OK, so this one, we start with a thermofield double geometry, and we want to act on it with a perturbation at time 0. I've chosen a boost frame so that time 0 is here. It looks like it's an early time, but OK, that's the time translation. So the perturbation acting at that time, it creates a particle close to the boundary. And if we evolve forwards, the particle falls into the black hole and follows a trajectory roughly like this. Actually, there's a whole wave function that describes it, but this is a kind of classical approximation to what happens. If you go into the past, it would look like that. So that's the complete description of this state. OK, now let's do the same thing for the other state. So we do another animation. Yeah. Why did I draw the arrow? Yeah, both ways. It's just whether you evolve backwards. So let me try to explain this diagram better. Thank you for asking. What I mean by this is we know what the state looks like at this late time. This late time, there's a V particle here and a W particle here. And if you were to evolve that state forwards, the V particle goes further in, the W particle goes further out. If you evolve it backwards in time, V particle moves in, W particle moves in. So if we evolve a little bit farther, it's going to look like this. And there's some kind of collision that's going to take place in the past. So what this state looks like is it looks like maybe some collision took place in the past, and we're now describing what happened afterwards. That's an out state. OK, now the same deal. So this is the thermofield double. Nothing has changed. For this one, we're supposed to act with W of t on the thermofield double. So that creates this particle up here. And if we left it to its own devices, it would do that. And now we want to act V of 0, W of t, thermofield double. And now it's convenient to look at this slice at an early time, because now that's the slice where the particle that exists is kind of far away from the boundary. So if we do that, then we're going to end up with a particle here, and then we add another particle from the boundary here. And so again, we should draw these two kinds of arrows. If we evolve into the future, they're going to come up here, and some kind of a collision is going to take place. So this is an in state. So the full OTOC is an inner product of an in state and an out state. And OK, I forget exactly which OTOC I defined, but the OTOC, it's an inner product of an in state and an out state, or maybe out within. I forget how I defined it. So this is basically a scattering amplitude that's taking place for some scattering processes taking place near the middle of this diagram, near the what's called the bifurcate horizon, the place where the two horizons intersect. And for a gravitational scattering problem, the most important thing to know to predict what is going to happen in the scattering is the center of mass collision energy squared. This is what's called the Mandelstam S parameter, which is the center of mass energy squared. So that's a Lorentz invariant quantity, and we can compute it in whatever frame we want. So to compute it, it's actually convenient to use a frame where t equals 0 is back where it should be in the middle of the diagram, and time t is up here. So the V operator is creates some particle like this. The W operator creates some particle like this. We're trying to estimate the center of mass energy for the collision. So the energy components, the momentum components of the V particle that's created by the V operator, in this frame will be of order 1. So the momentum components for the V operator, or the V particle, will be order 1. Or more precisely, they'll be order 1. They will not depend on this time t. What about the momentum components for the W particle? Well, they would be order 1 in this frame where time t was here. And to go to that frame from this one, we should apply a boost. That's this time the fact that the time translation of the black hole geometry is a boost. It's a Lorentz boost. And so the rapidity of the Lorentz boost is 2 pi over beta times t. So the momentum components of this thing will be like e to the plus or minus 2 pi over beta times t. And in particular, the center of mass energy squared, which will be a kind of a product between these momentum components and those momentum components. The conclusion of this discussion is that this thing will be proportional to e to the 2 pi over beta times t. So that's a big deal because it's growing exponentially in time. The center of mass energy in this collision is growing exponentially in time. And yeah.
It's Minkowski space in this discussion.
The region near the bifurcate horizon. The region near the bifurcate horizon is being treated like it's Minkowski space. Because the collision takes place very close to that.
Aren't you assuming that the transverse distance is big?
No, I'm not. But even if it is, the important thing is that the RT plane it resembles Minkowski space close to the horizon. So the 2 dimensions that are not the transverse direction. That's what's important for this kinematics. The fact that it's not Minkowski space is important. It changes, for example, the graviton exchange because it changes the graviton propagator, and it changes qualitatively the answer. But the manipulations we're doing are still correct because they're only relying on the Minkowski-like property of the region near the bifurcation surface and R and T. Yeah. Okay. So this is big, and if we go back to this equation up here, it says that the interactions between particles, interaction is weak if the number of boundary degrees of freedom is large. So these particles, the gravitational coupling is very small. But normally you can ignore gravitational interactions. That's what I told you for the 2-point function. Forget about interactions. But here we have a center of mass energy that's growing exponentially in time, so we cannot ignore the gravitational interactions. So basically what happens is the scattering amplitude goes to 0 for sufficiently high energies, and we get this kind of a curve. And I can explain the leading correction to 1. So the leading correction to 1 is like OTOC of t is like 1 plus I times some stuff. The stuff is g Newton times the center of mass energy S times, well, since Tom asked a question about this, I should put some function of the impact parameter, which I'm suppressing this this aspect. So it starts out like this. And if we translate this term here into the time t and the number of degrees of freedom, this looks like 1 over the number of degrees of freedom times e to the 2 pi over beta times t. So there's a small correction to 1, but it's exponentially growing in time. And at a time that is logarithmic in the number of degrees of freedom, the correction becomes big, and this function starts to decay. You might be confused because I have an I here, and that is a property of the theory of gravity. If we studied the out-of-time order correlator in a more generic theory, like the SYK model at finite temperature or a stringy black hole, then we would expect to get something like 1 minus e to the minus, okay, I pi over 2 times lambda over 2 pi times e to the lambda times t divided by n. So in the gravity case, we have this exponent is called the Lyapunov exponent. It's 2 pi over beta. And more generally, lambda is less than or equal to 2 pi over beta. And generically, this will be have a negative real part. So the function will decrease at first order in this perturbation. In gravity, to find that the absolute value of this thing decreases, you have to go to second order. And there's some interesting thing there that has not been completely understood. Like, I think Kitaev was very interested in this for maybe even a couple of years. Like, his idea was that in gravity, this I is a symptom of some kind of a coherent effect. Like the OTOC, it's an amplitude for something, some coherent thing to propagate. Whereas in a more generic chaotic system, where we have a lambda less than 2 pi over beta, the real part of this thing represents some kind of an incoherent effect, like a probability for some scrambling to happen, a probability that the operator has grown to some size. Whereas this I here is like some kind of coherent propagation. But I think it's safe to say that, like, I think even Kitaev did not really get to the bottom of this, and there's more probably to be said about the about that issue. Okay. Yeah. Let me move on. So next we'll discuss eigenvalue statistics. So this is part C from our list of symptoms of many-body quantum chaos. So let's imagine that we have some quantum system, and we plot the density of states as a function of energy. This is rho. And then let's zoom in on some little region here. Zooming on that little region, we find that the smooth-looking density of states resolves to a bunch of delta functions. And these delta functions are at, of course, the specific energy eigenvalues. The Bohigas-Giannoni-Schmidt conjecture is that the spectrum of these numbers, they're not random numbers. They're not like you threw darts at the energy axis. They repel each other, and they have the correlated statistics of eigenvalues of a random matrix. So a property of that is familiar is that the nearest neighbors repel each other and have this Wigner-like distribution. But another sort of easier to think about aspect of this can be stated at the level of the continuum density, which is that this should have a repulsive anti-correlation. So if the energies are fairly large, so many eigenvalues spaced, it's still true that a little overdensity of eigenvalues here is correlated with a little underdensity somewhere nearby. So that's why we have a minus sign here, and the particular power is a computation in random matrix theory. So you can translate that correlation into something called the spectral form, into a behavior of something called the spectral form factor. The spectral form factor has been studied for decades in literature on quantum chaos. And what it is it is z of beta plus it times z of beta minus it. So we take the thermal partition function and analytically continue it in time, in beta. And this thing we're going to smooth out somehow by, for example, integrating over time a little bit. And as a function of time, it looks like this. So it starts out really big, like e to the 2s. And then it decreases because we're introducing phases into the sum over energy eigenstates. It decreases. And then at some point, it starts to grow linearly and then plateau at a value of order e to the s at a time of order e to the s. So that tells you that this plateau region is about of order t. So this function, this linear thing here is called the ramp, and it is the Fourier transform of that. So that repulsive anticorrelation, kind of long distance repulsive anticorrelation, translates to this linear growth of the spectral form factor. Okay. So to compute this in using the black hole, what we're supposed to do is we're supposed to compute 2 copies of this thermal partition function. And the rule for that is, we want to discuss now grav of z of beta plus it, z of beta minus it. So to do that, we're supposed to take take 2 circles, and they're going to be complexified circles. So this one is beta plus it, and this other circle is beta minus it. And then we try to fill them in different ways by solutions to Einstein's equations. So one way you can fill them in is you just fill them in like this, like two disks. Here we also have product with this sphere. So you fill in the 2 disks, and that gives something that decays with time and reproduces this part of the curve. Another way that you can fill it in is with what's called a wormhole, where you replace the 2 disks by a cylinder. So we could fill in these 2 disks. We could fill them in topologically with some kind of cylinder. So this is continuing the equation that was up there. And the claim is that that cylinder gives this thing. And the point about this that is relevant to this discussion is that that was discovered by searching for it, by quantum chaos predicts this, so we should find something like that in gravity. So this is very much in the direction of quantum chaos informing us about solutions to general relativity and their interpretation. So let me describe what this wormhole is. So you start with this real-time black hole. You start with a slice at t equals 0. And you also consider a slice at time t. And you take everything in between them. And you periodically identify the 2 slices. So that's something that kind of looks like 2 cones glued together at the tip. And the boundaries of the cones, let's see what time interval is associated to the boundaries of the cones. So let's do this side here. So between 0 and t, we have some interval of time that is t. So this is like a interval of imaginary time that is equal to I times t. On the right boundary, we have circumference I times t. On the left boundary, we have circumference minus I times t. So the boundaries that we have here correspond to 2 circles, one of size it and one of size minus it. And so that is exactly the kind of boundary conditions you want to fill this thing in if beta is equal to 0. Okay. Yeah. Yes. Good. Yeah, so this point here looks singular, and it sort of is and is not singular. So a statement, that's because there's a small deformation of the geometry by an I epsilon that is completely smooth. So the interpretation of that small deformation by I epsilon is not completely clear. And people in the blue group can, in the discussion, can hear Juan's views on this. He wrote an interesting paper about this, and I think it's, on the one hand, yeah. Let me not say more about it now, but yeah. So let's try to compute the contribution of this wormhole. So the contribution of this wormhole should be e to the minus the action times, in a leading approximation, some kind of one-loop determinant describing small fluctuations around this solution. And the one-loop determinant breaks up into two parts. There's a contribution from zero modes and a contribution from non-zero modes. Okay. So first of all, the on-shell action S star for this geometry is 0. It's 0 because it is proportional to the space-time volume, and the space-time volume of this thing is 0. It has imaginary volume on one side and minus imaginary volume on the other side. So that action is 0. The one-loop determinant, the non-zero modes, so let me describe these two. The non-zero modes look like trace over non-zero mode Hilbert space of e to the minus I times t times k, the operator that generates this, this transformation. So, and the spectrum of this thing is, this trace is not well defined, but the trace, there's a nearby thing that is well defined, which is e to the minus I t times k minus I epsilon times some other operator that is related to the smoothing of this singular part of the double cone. And this becomes a sum over quasi-normal modes. And so this approaches, well, 1 plus a sum over quasi-normal modes. So this approach is 1. So the integral over non-zero modes for a large time t becomes just 1. And the integral over zero modes becomes a product of two factors. One is a sum over what energy of black hole you started with. So there's an integral over energies, and then there's a factor of t. And the factor of t arises because you can take one boundary and rotate it relative to the other boundary. And that gives you a compact zero mode whose volume is t, just the size of the total boundary that you can rotate. So the entire answer for this thing gives a factor of t times the integral over energies, and that is exactly the answer that is predicted by random matrix theory. Okay, there's a puzzle about this. There are several puzzles about this. One of them is the slightly suspicious singular part here, and another one is the fact that we appear to have a weird situation that gravitational computation of this times this is not equal to grav of z of beta plus it times grav of z of beta minus it. This is a puzzling thing associated to wormholes. It goes back to papers by Witten and Yao and Maldacen and Mao. So it's kind of a kind of a confusing aspect of including wormholes. Including wormholes in gravitational path integral is a little bit like making a deal with the devil, where like you get very interesting things, but there's this factorization puzzle that has not been resolved. So the spectrum of possible resolutions of this factorization puzzle ranges from it's fine, gravity just computes an average over quantum theories on one hand, to wormholes should never be included on the other hand, and other various possible positions in between. And this is a unresolved problem in quantum gravity. Yeah.
So semi-classical calculation, right? So is it trustable? The action is not large.
Yeah. Yes. That means it gives a small correction to the two disks, which have a large negative action for short times. So the fact that the action is large or small just means the answer gives a big or small contribution. It doesn't mean whether it's trustworthy or not trustworthy. Whether it's trustworthy or not trustworthy depends on like higher order expansions of the action around that saddle point. And the fluctuations are small if time is large. Yeah.
You emphasized the case that beta plus IT was imaginary. But if you take beta plus IT to be real, would this just be the smooth Euclidean double trumpet or whatever?
Yeah, that's not a classical solution. So to have a classical solution, you should have opposite betas on the two sides. So the classical solution is for this case, IT and minus IT. Okay, yes.
The coefficient is different from this saddle calculation, right?
The double trumpet, sorry, say it again?
If I just consider double trumpet, then I analytic continue like to beta plus IT, beta minus IT.
Yes.
They both grow linearly, but the coefficient is different.
No, the coefficient, you mean the double trumpet in JT gravity? Yeah, the coefficient is the same. Since that refers to some things I have not discussed, let me explain it to you privately afterwards. But yes, the coefficient is the same. Yes.
It looks like in higher dimensions, you could do the same calculation, just dragging the sphere along as a factor.
Yeah, that was implicit here. Yeah, higher dimensions, rotating black holes, charged black, it's the same. Yeah. Okay, I don't have time for the last part, so let me say what I was going to talk about. I was going to talk about the statistics of eigenvectors. And there are two things that I think are interesting there that I wanted to explain. And you can discuss them in discussion groups if you're in the right group. So one of them is the statistics of the matrix elements of an operator between energy eigenstates. And random matrix, quantum chaos predicts that these should be kind of random matrices, close to Gaussian distributed. And this can be shown in 3D gravity now. So some techniques developed in part by Tom Hartman and others to compute partition functions, ultimately like exactly for given topology in 3D gravity, can be used to compute statistics of these matrix elements. And you find that they're approximately Gaussian with some interesting non-Gaussian corrections. And so that gives some kind of a souped up theory of ETH, some kind of non-Gaussian theory of ETH associated to 3D gravity computations. And this is a very interesting active area in high energy theories to try to understand what is the meaning of 3D gravity and the souped up ETH exact computations. So you should, Tom, you should tell people about that in your group. The other thing, Tom and Juan are in the same group, right? No? Oh, good. Okay, so something, well, okay. Something you could ask Juan about is another aspect, which is this of random eigenvectors, which is that if you start with a simple operator, so prediction of quantum chaos is you start with a simple operator and you look at it in some energy eigenbasis, then it should look like a random matrix. So if we take an operator, like a simple operator W, and we put a projector onto some microcanonical part of the energy eigenbasis, then the result is some operator that looks like a, if the projector is in a small enough dimension, it looks like a random Gaussian distributed random operator. And so in a paper, Lin, Malesana, Rosenberg, and Sean, they discuss this for a kind of a crazy case where the projector projects to a particular microcanonical window which corresponds to ground states of a supersymmetric black hole or supersymmetric quantum mechanical system. So they consider an operator projected to the BPS subspace of ground states. And their conclusion is that if these states are described by a black hole, this is still true. It looks like a random matrix. And this is very interesting because your idea about chaos, quantum chaos, should somehow apply to high energy things, and certainly to like time evolution, like the butterfly effect, thermalizations. These are things about time evolution. And somehow the idea is that for a black hole, it's so chaotic that even the zero energy stuff satisfies this, has this symptom of quantum chaos. And so there's some work, but yeah.
Zero energy degeneracy.
Yes, yes, yes. So, well, yes and no. So if you don't have a lot of exact degeneracy, you just have a lot of, low energy states, they're not exactly degenerate, then it's still true. You can consider some late time projector, so some low energy projector, and it looks like a random matrix. So even the low energy states, they're chaotic. But the more extreme version of that is if you happen to have a supersymmetric theory with a large exact degeneracy, then it's also true for those literal degenerate ground states. And well, depending on your expectations, that's kind of surprising. And yeah, there's some ideas of how to use this to distinguish black holes from other types of systems. Yeah.
Because if they're exactly degenerate, I could just look at as a matrix in the basis in which W is diagonal, and it wouldn't look like a random matrix, would it?
Well, the projector is complicated in that basis. Yeah, so, sorry. So W is some simple operator, has nothing to do with the ground states. Yeah. Oh, yeah, right. So yeah, you can diagonalize W tilde, but yes. So yeah, it's kind of weird. You can turn this question about eigenvectors into a question about eigenvalues again by studying the spectrum of this thing. So like we cannot get away from random matrix eigenvalues. Okay, I'm done. I'm over time, so I will not try to summarize. Thank you.
Looking at the fallout of the 2-point function in your first example of the to check the thermalization, is there a way to see the time at which the particle crosses the black hole horizon sharply?
No.
No, there's not. The problem is that the time when it crosses the black hole, it depends. It's not identified with a boundary time. It's you can pick different. So here's the boundary, here's the horizon, here's the particle. At this time on the boundary, I could pick a slice into the bulk like this, or I could pick a slice into the bulk like this. And according to one slice, the particle has already fallen in, and according to the other slice, it has not. So there is no invariant boundary notion of when it crosses the horizon.
Okay, now let's go to coffee.